All right, hello everybody. Welcome back to the Algebraic Topology seminar. Today we're going to try and finish covering spaces because um, personally I kind of don't like them. Um, we went through the problems, so I'll probably just post some of these. I'll like maybe tech it up and put it on my GitHub or something. Um, but yeah, we went through the problems that were discussed at the end of the last lecture. So, next what we're talking about is called lifting properties. Um, and so covering spaces are defined in fairly geometric terms as maps um, P from x tilde to x that are local homomorphisms in a rather strong sense. But from the viewpoint of algebraic topology, the distinctive feature of covering spaces is their behavior with respect to lifting of maps. Recall the terminology from the proof of theorem 1.7 that a lift of a map f from y to x is a map f tilde from y to x tilde such that p f tilde is equal to f. We will describe three special lifting properties of covering spaces and derive a few applications of these. So first we have the homotopy lifting property, or covering homotopy property, which is given a covering space P from x tilde to x, a homotopy ft from y to x, and a map f not tilde from y to x tilde lifting. I think it means ft. No, lifting f not. Um, then there exists a unique homotopy, ft tilde from y to x tilde of f not tilde. That lifts ft. Okay, that's weird. So we have a covering space. We have a homotopy from y to x. We have a map y to x tilde to x. So ft is here. And then we have larger ft. And then we have f naught. Wait, what? Of a homotopy and a map. Okay. F naught that lifts F naught What's F naught? Am I dumb?
Maybe it means F not tilde.
I think
No, because
maybe,
no, because it says it differently actually in the definition.
yeah. So I think we have P, but then maybe it's that. Then there's a unique homotopy of F naught that lifts FT. So the thing that's induced, hold on, let me put the thing that's induced in blue. Okay. And it's a lift with respect to P. So what is, hold on, let me look at the last lecture's notes. So like an example would be like this would be X tilde and this would be, or it would be, this would be Y, this would be X, no, X tilde to X. Oh, wait. What is happening? Um,
I will say that the proof for this proposition, uh, they give as part of the theorem 1.7, which was in. See if I can look at it.
I mean, I'm seeing how this is, like, how this would exist. I'm just wondering why it's important. There's a homotopy of F naught of this green thing, right? Like, we have a homotopy. Hopefully that's clear that that's a homotopy between F naught and FT that lifts FT, which I guess is equal to the composition PFT. But then this is equal to P. I don't know. I guess I'm just lifting, or I guess I'm just not understanding the importance of the lift. Maybe that'll become obvious the further we get. So, and then taking y to be a point makes this the path lifting property for a covering space P from x tilde to x, i.e. for each path f from I to x, each lift x naught of the starting point. I guess maybe I shouldn't have said P. There exists a unique path f tilde from I to x tilde, lifting f starting at x naught. And then as a corollary, every lift of a constant path is constant. Let me just Google something real quick. Um, okay. Oh, okay. So this lets us the only thing that a lift does is it lifts it into a covering space that has like basically a structure that we can study with group theory without having to worry about like loopiness. So basically like questions about homotopy and X become like path tracking problems of lifts in the covering space. Does that make sense?
Um, kind of. I don't know if you could like maybe we'll kind of get to that sort of how it'll help us with group theory, but uh I'm not sort of seeing it right now.
Um, okay. I have a good example,
Okay.
I think. So an example is P from R to S1, which sends T to E to the 2 pi I T. Um, and so basically, and if we consider just one loop, what this looks like is so one loop on S1 is T in the unit interval. Um, and so like the lift of one loop is to insert R to the unit interval to the circle, where basically like we have this map that has all of the loops, but we can look at like um, we can look at like one loop at a time, I guess.
Okay.
And then the collection of each of these things going from I, like if we call it gamma, let's just say, where gamma of t is basically equal to um, if gamma of t, well, no, this would be p. The lift happens here, and so then gamma of t gets lifted to a homotopy like that, which is basically nt for n in Z. And then gamma of t through p ends up giving you the structure that pi 1 of S1 is the collection of unique lifts indexed by n.
Okay. All right.
And so I think it's what it's trying to get at is the concept of indexing, and that if we were to index by like z mod p or something, then like this would be a much more meaningful index.
Okay. All right. That makes a little more sense if you put it
Yeah.
if you put it like yeah. Okay. All
So
right.
like the idea is like we always get this unique thing that gives us an index. Because when I looked up like how do covering spaces show up in homology or cohomology, we're going to be using covering spaces to calculate like homology groups. And the way that like they help us calculate things is with the notion of indexing.
Okay. Okay. That makes sense. Okay. Yeah.
So I think the thrust of all of this is we want to keep track of indexes. Covering spaces give us a way to do that, uh, and existence and uniqueness are guaranteed.
Gotcha. All
So
right.
I'll even write that down because that's helpful. We want a way to index pi 1 of x. Um, and then existence of lifts, and then uniqueness. And when I say lift, it's really just a way to index pi 1.
Gotcha.
And so like every constant path is contractible. And so since it's contractible to a constant point, it's contractible to a base point. And that's why like there's this corollary that every lift of a constant path is constant. Like if you have a constant path, it's null homotopic. If it's null homotopic, then it has a constant index. Um yeah. So a simple application is the map P star from pi 1 to pi 1 induced by a covering space is injective. That seems like it would be the opposite. It seems like it would be surjective, right?
Um, hmm. Yeah.
No, no, definitely not actually. Because like in the example up here, if we're looking just at the sphere and we're looking in here as the lift, like if this is the lifting space, then if we have like a unit interval from like pi over 2 to pi, then like this would map back into the lift as just 1/2 to 1. So it is injective, but if we mapped it all the way back through the inverse image of the lift, it wouldn't be. Does that make sense?
Yeah.
Or I guess it would be n times that interval. So no, this is injective. Um, and then furthermore, the image subgroup P star of pi 1 in pi 1 of x comma x naught consists of homotopy classes of loops in x based at x naught whose lifts to x starting at x naught are loops. Yeah, I think that's pretty fair. Like I feel like that just kind of makes sense. I think the discombobulating part is that well no, I guess it's not because it's a homomorphism, so the image is a normal subgroup. So yeah, I mean that's perfectly reasonable. Does that make sense to you?
Yeah, I'm just looking through the proof here for
Yeah, and I think he does it by showing that the kernel is trivial. Yeah.
yeah.
Yeah. I don't know. Do you think having looked at the proof it's worth writing down or just continue a little bit?
We can move on.
Okay. So the following proposition is oh, I guess it starts with the definition. Um, if P like so is a covering space, then the cardinality of P inverse of X is locally constant over big X. Well, I guess I'll rewrite this to clarify that that is a small x. Um, if big X is connected, um, its cardinality is constant over all X. P inverse of X is number of sheets of the covering. Yeah, and so this is our way of keeping track of the index. And I think like an example of this being useful in real life is in complex analysis, with like Cauchy's integral formula, um, with like the winding number of like, I don't know, some analytic function, um, where like you like I guess for like the exponential or the log or trig functions, you have an infinite winding number. But if you had like a cuspoidal kind of thing that had a pole in here, then like you end up getting that the integral, if this is a contour C, the integral of some analytic function f of z dz is equal to 2 pi I um, times the residue at that point. But then this is determined by the winding number of C. So I think that like this is an example of like we could calculate something with the winding number from the number of sheets of a cover space. And then yeah, this leads to a proposition. Um, the number of sheets of a covering space is equal to the index and I'm just going to abbreviate this. And this makes a lot of sense. Like this was the whole motivation up here. It's important also to know about the existence and uniqueness of lifts, of general maps, not just homotopies. For the existence of lifts for general maps has um, given a covering space and map f from y not with y path connected and locally path connected we'll switch colors. A lift. And this makes a lot of sense. This is a pretty nice criterion. So we have, I'll draw out the little diagram for it. So this is Y, if this is the cover, and we are given P, oh, well, I guess that needs that. And we have one. We have F. Then that exists if and only if the induced map from the functor F star that takes well, okay, no, this is the pi1 functor. Gets mapped over to pi1 of y has this getting mapped over and then this is the real criteria. So that if we have the same functorial thing going on, what's P star? P star goes, oh, I was wrong. Hold on. There is this going on, but there's also this. I'm just going to erase this, copy that. There we go. That if this is pi1 here and this is pi1 here, that F star so if this is P star goes here, that, and I'll put this as this lands. Okay. And since the existence of this thing is debatable, I'm going to put it like that. Okay, does this diagram make sense?
Yeah, I mean, just look at the criterion and you pretty much follow it.
Yep. So, if we can show that this thing exists, it's the same thing as showing that this exists,
Yeah.
and vice versa. Okay, cool. Um, when we say that a certain property holds locally, such as being locally path connected, we shall mean that each point has an arbitrarily small open neighborhood with this property. Thus, for y to be locally path connected means that for each point and neighborhood, there's an open neighborhood containing both, um, that is path connected. So, yeah. Um, for the goal of hopefully getting through to the deck transformations today, I'm gonna omit the proof if that's okay with you.
Yeah, I think it would be nice to go through. Um, they have a
Okay.
diagram kind of outlined here, but if we want to, yeah, I agree that, um,
We can go through it if you want to.
no, no, I agree that we're kind of at a time crunch to get through this stuff, and yeah, like this could be something that we go over in our own time or something like that.
Yeah, sure. Let me just mark it down in my book as
Yeah,
that then.
I'll do the same as well.
Okay. Cool. Um, so next we have the unique lifting property. Um, so given with two lifts that agree on one point in y, if y is connected, um, f1 is equal to f2. And I think that there's kind of an interesting connection here to algebraic geometry. Um, kind of the notion of like if two morphisms agree on like an open subset, that they have to be the same morphism. But I don't know if that's actually connected, but I think it might be. Um, I don't know. The proof doesn't look too bad, so let's go through this one. I feel bad because we keep bumping proofs. So let y and y with y and u open, or with f of y and u open in x, such that p inverse of u, say, coproduct of open sets each mapped to U by P. And let U1, U2 be the U alphas containing F1 of Y and F2 of Y, respectively, since F1, F2 are continuous, there exists N of Y such that F1 restricted to N is equal to U1, and I'll just say UI and FI. If they're different, oh yeah, if F1 is not F2, then U1 isn't U2. So U1 intersect U2 is the empty set. Oh, U1 on N. Wait, hold on. Oh, wait. So U1, yeah, and F1 on N is not equal to F2 on N. Alternatively, if F1 is equal to F2, then U1 equals U2. So F1 on N equals F2 on N to satisfy continuity. And since P F1 is equal to P F2, and P is injective on U1 equals U2. Then set of points where F1 agrees with F2 and Y is both open and closed. And therefore it's either Y or the empty set. Huh, that's pretty elegant proof. I like that. Any questions on that?
Nope.
Okay. So now we come to a section on classification. So we consider next the problem of classifying all of the different covering spaces of a fixed space. Since the whole chapter is about paths, it should not be surprising that we will restrict attention to spaces that are at least locally path connected. Path components of X are then the same as components, and for the purpose of classifying the covering spaces of X, there is no loss in assuming that X is connected. The main thrust of the classification will be the Galois correspondence between connected covering spaces of X and subgroups of pi1 of x. But when this is finished, we will also describe a different method of classification that includes disconnected covariance spaces as well. So Galois correspondence rises from a function that assigns to each covariance space the subgroup I'm just gonna, since we're assuming connectedness, I'm gonna remove the base point from everything. And that this is a subgroup of pi1 of x. So, and really this is a functor, right? Like, definitely a functor. We want to consider whether or not this is a surjective function slash full functor. That is, whether every subgroup of pi1 of x is realized as p star of pi1 of tilde x. So, want one is every h realized as some p star pi1 covariance space for some p. In particular, is the trivial group realized. And we know that p star is always injective. This amounts to asking does x have a simply connected covariance space? Okay. So, I'm going to say this is a proposition. X has a if for all x in x, there exists u such that the inclusion-induced map pi1 from u at x to pi1 is trivial. Um, we say X is semi-locally simply connected. And I don't know if this is the only condition, so I'm not sure that that's true. um, so to see if this is really necessary, there's an example. Um, covering space is a simply connected covering space. um, X X. There exists a neighborhood U with a lift which has a homeomorphic projection to U by P since each loop in U lifts to a loop. Um, which is null homotopic and since it's um, um, the original loop must be null homotopic as well. Oh, that's kind of nice. That's actually like a very interesting characterization going on. Um, a locally simply connected space is certainly semi-locally simply connected. CW complexes have the much stronger property of being locally contractible. Um, an example of a space that is not semi-locally simply connected is the shrinking wedge of circles. Um, on the other hand, the cone is semi-locally simply connected since it's contractible, but it is not locally simply connected. Huh. It's pretty interesting. Um, tell you what, would you be cool to take a 5 minute break real quick?
Yep, we can go ahead and do that.
Okay. Be back at 2:07.
Gotcha.
All right, I'm back. Are you back?
Yep.
Cool. So what we're gonna do is we're going to show how to construct a simply connected covering space of X if X is path connected, locally path connected, and semi-locally simply connected. Oh my God, there's so many words. Um,
Do you want to like abbreviate uh
okay.
some of this
So
stuff here?
yeah, I'm gonna say so theorem let X be path connected locally simply connected. And the key thing here is that this is an and. We can construct a simply connected covering space of X. And so I want to try and write this out in just like block bullets so that it's just kind of an algorithm that we can refer back to. Um so to motivate the construction, let P be a simply connected covering space. Then each point in the domain of the cover can be joined to the base point by a unique homotopy class of paths. So we can view points of the domain of the covering space as homotopy classes of paths starting at x naught. The advantage of this is that by the homotopy lifting property, homotopy classes of paths in the domain of the cover starting at the base point of the cover are the same as homotopy classes of paths in X starting at x naught. This gives a way of describing the cover in terms of X. So given all of our assumptions, we're going to define X tilde to be the set of paths starting at x naught. Um, then let this map um this to its endpoint, and it's a surjection. Before we define a topology on this space, we make a few preliminary observations. Um, so let script U be the collection of path connected open sets in X such that um, pi1 of u to pi1 of x is trivial. Note that if the map is trivial for one choice of base point, it works for all of them. Subsets are also in U. This is a basis for the topology on X, given our assumptions. So then for every U and gamma in X from X naught to A in U, let U of the class gamma be the set of gamma composed with eta such that eta is a path in U with eta of 0 equal to gamma of 1, which is really equal to P gamma. Although, actually, we don't want to define that way. Observe that this is a surjection. And it's also injective. So this is a bijection. Another property is that you have the class of gamma and I guess that's just kind of how it works, right? And so then gamma is a basis for the topology on X tilde. And then there's a whole proof for the fact that I guess so. Let the base point constant loops or constant paths. Then pi1 is equal to 0. And that's our construction. So all in all, not terrible, just a lot of words. um, and this is endowed by the topology for you. Um, in here, we really need to prove that this P is continuous, but it's just kind of a standard proof, I think. Is this pretty reasonable the way I've set it up, Zach?
Yeah, did you get like I think I'm falling for I got 3 and I'm missing how you got 4.
4 was on halfway through page 64, assuming you have the paper copy.
Yeah, let's see here. Oh, I see. All right, I know I just completely missed it. Sorry.
And then I skipped, so there's a whole thing showing that that forms a basis for the topology
Right,
on
right.
X
Okay,
tilde.
that's what
I
I
just jumped over
okay.
that.
That's
And
what I
then the
got tripped
thing
up.
about showing that pi1 is actually 0, I also jumped over because my eyes are glazing over.
Gotcha,
I
gotcha.
don't, the thing I've found that I actually dislike about this book is that the text is too close together and the font is one size too small, and so my
Yeah.
eyes get really tired.
Okay. Yeah, no, yeah, it was actually just like from 4 to like 4.2. Like I had the same issue. Okay. Now I
Okay,
see where you got
this
from 4 to 5. Yeah, I see it.
this
All right.
book is going to make me get glasses. Um, okay. In concrete cases, one usually constructs a simply connected covering space with much more direct methods. That's why I'm talking so slowly, is I keep like messing up words because my brain is just like, what am I reading?
Yeah.
Like genuinely, I'm just gonna start saying AI slop. Like, um, yeah. So then there's an example of a more direct way of constructing simply connected covering spaces. Um, so for example, um, more directly, if X is the union of subspaces A and B, for which we already have the things that we want, then there exists simply connected covering space by assembling copies of the two. So as an example, wedge product of two circles. Um, then the covering space is, oh, this is the example that I gave previously. When we first started like being like, why do we care about covering spaces? Um, Yeah. Has this just sends t and w to e to the 2 pi I t the same way it did earlier, um, with tw in I cross I. Um, and if you want to do this for a cylinder rather than a sphere, then you are given an identification M and N, and there's an associated thing. Um, and what this looks like is like just drawing a bunch of lines between things. Like if this is y, x, x, and it's kind of like, I don't know. I'm not good at drawing these things, but hopefully from the intuition that I gave earlier, this makes sense in terms of we can think of things with an index. And the modular case that I was talking about when I like first motivated this stuff, like up here, with like, well, what if this is z mod m, is for a cylinder with an identification under e to the 2 pi I over m z. Um, and that's detailed in the book, so I won't go through that. Um, yeah. That looks like a particularly messy example. The figure, for example, hold on, 1.29. Where is example? Oh, God. Yeah, I don't want to do that. Um, I couldn't draw that in the first place, and I definitely can't draw the covering space.
You got it, then. That looks so complicated.
Holy. um, I'm gonna pretend like this page and a half doesn't exist. That's gonna be the
Fair.
plan. It's basically just following the process for an example, but I'm gonna take a wild guess based off of how easy the problems were at the last section. That there's like an easy set of questions on, hey, let's build some simply connected covering spaces instead of um, the example of pain and suffering.
Yeah.
And so let's just move on.
All right.
We will live to fight another day. Um, so the hypothesis for constructing simply connected covering spaces of X, in fact, suffices for constructing covering spaces realizing arbitrary subgroups of pi 1 of X. So, um, I'm just guessing that this is like a correspondence sort of theorem. PCLPC SLSC. Dude, this looks like a new motto
No, that I was just about to say, yeah,
from
it's
like
over. Like a
chemistry.
password. Yeah.
It's like Dude, I'm gonna start using this as like my password. Like nobody's gonna break it.
No, no one will ever know.
Yeah. Um. Then I just need to write it out first, and then I can talk. Okay. So X is the type of thing that we like working with. For every subgroup, there exists a covering space such that the the map. This is just a morphism of shoes. Oh, okay, that's okay. I understand this. Um, sorry. I guess this is. Hmm. It's kind of suspicious that this is called XH. Um, um, yeah. That's actually a really nice property. This is this is a really nice property. Um, okay. Yeah. So the proof is not terrible, so we're gonna do it. Um, and what? I guess X H injects to X tilde. Um, I'm a little confused. Maybe it'll work itself out. Okay. Then it's an no, it's not an injection. It's just an inclusion. So any 2 points in basic neighborhoods are identified in XH, and they identify their entire neighborhood. And then the idea is that because of the conditions here, we can move neighborhoods around. I don't know. I don't feel like I'm explaining this very well, but I also don't feel like I have the mental capacity to like give helpful exposition.
Yeah.
Zach, do you
I,
have anything?
I'm just curious as to why when we have the map xh to x that's a covering space.
Well, it's a covering space because it's a quotient of another covering space. And then yeah, the quotient of this other covering space still gives like all of the conditions that we need.
Okay.
I don't know. I don't think that's a good answer, but is that
Um,
like the conditions that we need
did they
for a
just like
covering
follow, yeah,
space?
did they just follow through from the quotient space?
Yeah, like we kind of just want like the existence of a lift. And
I
then
see.
we're given this other covering space. And so we're taking lifts and then we're taking quotients of collections of lifts. And so all we're
Okay.
really doing is kind of like bundling together lifts by open neighborhoods.
Okay.
So like the same way that you have a quotient topology, if you were to put like all of the possible lifts on each open subset and you were to bundle that together, then you can glue them together under this equivalence relation.
Okay. Okay.
And if you bot out by that relation, then you still get like you just get bundles of relations that identify open neighborhoods in the topology that's induced on X tilde.
Right.
I don't know. I'm kind of like I don't know how to explain it in like an AT way, but I could do it with AG. Like I guess the picture is that if you have X and you have X tilde and you have some open partitions of X tilde, then like this partition here identifies itself in the quotient space. Like if we have XH that goes like this, and we have this already, then we can like identify this to a specific thing here that collapses.
Oh, okay.
It's all of the it's all of like the gamma and gamma prime and eta. They all get identified with equivalence class gamma.
Gotcha.
And then that this maps, I guess really not here. Um, if this is this ends up going to pi 1 of x, and then this ends up going to h. But then this gets processed, this gets factored through, like this happens by pi 1. This has to have an extra pi 1 xh to there. Sorry, I'm mixing commutative diagrams and like domain diagrams, but like
Gotcha.
imagine a bubble layer.
Yeah, I got you.
Yeah. I don't know. Does that help?
Yeah, yeah, no, that makes more sense now. Okay.
So we're just like bundling things on open neighborhoods.
Yeah.
Um, so this takes care of the existence of covering spaces of X corresponding to all subgroups of pi 1 of X. Now we turn to the question of uniqueness. Mostly we are interested in uniqueness up to unique isomorphism, where an isomorphism between covering spaces is a homeomorphism that admits an inverse. Um, so I guess definition in from oops, wrong way. So diagram here. We have two covering spaces. Then we have this homeomorphism that commutes. Um, yeah. And then I guess the proposition that's important is that um, two covering spaces are isomorphic um, if and only if P1 star if their fundamental groups correspond. And these are really within pi 1 on X. And that seems like it just makes sense. Um, do we need to prove that to get like a better grip on isomorphism?
Yeah, I mean, the proof seems pretty simple.
Yeah.
So we can do it. Yeah.
Yeah, I mean, we just, say, okay, let um and what this maps. So that's direction one. And then direction two. Um, All right. I'm pretty happy with that. Sorry I didn't talk for any of that, but does that make sense?
Yeah.
The talking was just like getting to me. I don't know why. Just couldn't. Yeah. And so this is the first half of the classification theorem, um, which is um, that so basically we have the correspondence that we just proved, and we have existence and we have uniqueness. Um, the last statement actually follows from the proof that I ended up writing because I ignored base points. And so, yeah, if you're okay with that, then I am. I don't know. Do you feel like that's okay?
Yeah.
Okay. So a consequence of the lifting criterion is that a simply connected covering space of the long hellish mnemonic of X is a covering space of every other path connected covering space of X. A simply connected covering space of X is therefore called a universal cover. So prop slash definition a a universal cover. And actually, it's the universal cover because it's unique up to unique isomorphism. Um, this corresponds to the partial ordering by inclusion of corresponding subgroups of pi1 of x or conjugacy classes, there we go, of subgroups if base points are ignored. Cool. Okay, that's all I can do today. I can't do anymore. Um, we'll start up next time with representing covering spaces by permutations. Um, and then we will get into deck transformations and group actions. Any comments, questions, concerns before we turn off the recording?
No. No, we're good.
Cool.